Up to this point, the way that we find derivative functions is to apply a limit idea to a difference quotient. And that process becomes rather cumbersome when the function is of a certain type. And you may have found that out on the homework in the last section. Well, you'll be overjoyed to know that we're going to investigate in the next several sections some streamlined ways of finding the derivative of a function. Let's begin with a very simple constant function. And this rule is called the constant rule. If the function is a constant, then the derivative of the function is 0. If the function is a constant, the derivative is 0. If the function is a constant, the derivative is 0. That's all there is to it, just using several different notations here to indicate the same thing. This next idea is called the power rule, and the power rule says that if we're taking the derivative of x to the n power, then that derivative is nx to the n minus 1. Now, this is a general way to express things. The way it works with a real problem is like this. If the function is x to the 7th, then the derivative of x to the 7th is 7x to the 6th. And the way you'll probably recall this or make use of it is to think, well, this exponent is just going to move to a position of coefficient. And then the exponent is going to be replaced with a number that's one less than what we started with. And that's all you really have to recall in this. There's a nice proof of this in your textbook. I invite you to look at it. We're going to look at sort of the proof of a function in this family of functions in just a second. But first of all, I want you to look at a rather trivial version of this. If f of x is simply x, then applying this power rule, then the derivative is, well, let's see, the exponent is 1, so we'll have 1 as the coefficient, and then x to an exponent 1 less than this understood 1. So 1 minus 1 is 0, but x to the 0 is 1, so f prime of x is simply 1. Here's a function that we can apply this power rule to. I want to show the proof of how the power rule works on this function. We could apply the same kind of technique that I'm applying here to a kind of a general function that might be x to the n power. Now, but look at the technique that's involved here. We have to go through the limit process now to make this proof, but f prime of x is the limit of our difference quotient that we're so familiar with, and this f of x plus delta x means in the f function replace x plus delta x, so we have that binomial to the 4th power here. And then minus f of x means minus x to the 4th. And now here's where the fun begins. We have to expand this binomial. You see, we have to raise x plus delta x to the 4th power, and in the general kind of proof for this, we would have to be raising x plus delta x to the n power. Well, you recall from the days of algebra that this binomial expansion takes on a certain form. And that form begins this way. That is, we would have x plus delta x to the 4th power, and the first term of the expansion is going to be x to the 4th power. All right, the next term of the expansion has an exponent, has a coefficient that is 4, and x is raised to a power which is 1 smaller than this, and the other part of the binomial appears as a factor 1 time. And then as we march through, we consider coefficient and the exponents on these two parts of the binomial. So we have a coefficient times x to a power 1 less than this as we march through. You see, it'll be x to the 4th, x cubed, and the next one x squared, and then the next one x. You see, and it's just 1 less each time. And the other part of the binomial is appearing as a factor 1 additional time in each of the terms. So we have delta x here, delta x squared in the next term, then delta x cubed, then delta x4 to the 4th. So we have this kind of expansion. Now, notice I'm putting a blank here for the coefficients. There's a technique for calculating the coefficients, but we really don't need them here in the process, and we'll see why we don't need them in just a little bit. But notice that here we have delta x to the 4th, and that's the end of the expansion, and then I'm bringing down here minus x to the 4th from above. All right, now, let's see what happens. We have x to the 4th that we began with. We have minus x to the 4th all the way over on the end. Those two are going to take each other out. And now all of the other terms have delta x involved in them. And so this delta x in the denominator can take out one factor of delta x in all of these terms. So as I cancel this delta x, I'm left with 4x cubed. As I cancel one of these two factors of delta x, I still have a factor of delta x. And here I have a couple of factors of delta x left. And here I have three factors of delta x left. That's kind of important because now we have the limit as delta x approaches 0 of this polynomial. And as delta x approaches 0, all of these terms involving a factor of delta x will take off. They're out of here. They become 0. So all that's left is 4x cubed. And this kind of shows the how this power rule works from the limit process. And in general, you can see the general proof of this in your textbook. Well, the way the power rule works is like this. A lot of times in using the power rule, we have to rewrite our problem in a certain way. For example, in this one, y equals 1 over x to the fifth, I might spend a moment to try to put it into the form of y equals x to some exponent. And I can pretty easily do that by just moving that x to the numerator by forcing a negative exponent in there. This is really x to the negative 5 power. And now applying the power rule, I can calculate y prime to be, well, let's see, negative 5 moves to the coefficient position. And now I have x to a power 1 less than this. In other words, it is negative 5 minus 1, you see. And as I simplify, I get negative 6, so y prime then is negative 5 over x to the 6. Now in simplifying, you never want to leave an expression with a negative exponent on a variable. You always want to shift it around so that you'll be dealing with positive exponents. Here's another example of that rewriting business. We have g of x here is the cube root of x. First thing we'll do is write this as x to the 1/3 power. And now, taking the derivative, you know, by the power rule, we have 1/3 x to 1/3 minus 1. Well, 1/3 minus 1 is negative 2/3, and the negative exponent shifts this factor into the denominator. So we would have 1 over 3x to the 2/3 power. There are other ways to simplify this a little bit further if we want to, but this is sufficient for our purposes. The point here is that often we have to rewrite the function to begin with, and then we differentiate, and then we simplify the differentiation to complete the problem. As we proceed from problem to problem, not only in this section but all throughout this course, I suggest that you follow in your textbook and look at the examples in the textbook as well as the examples that I'm working here on the board. And as a matter of fact, as you see examples come up on the board, whenever you feel comfortable, it would behoove you to stop the tape, write the problem down, stop the tape, try the problem on your own, and come back and roll the tape to see how you performed and what your logic pattern was in performing that problem. It'll just help to solidify the whatever process we're talking about. All right, the next idea here is called the constant multiple rule. It works like this. The derivative of a constant times a function is the constant times the derivative of the function. Now, notice that it doesn't say that the derivative of a product is the derivative is the product of the derivatives of its factors. That is, it's not the derivative of 3 times the derivative of f of x. You see, and it's important not to think that way. It is the derivative of a, and we're going to think of this as a single term. That term happens to have a coefficient, so it's the coefficient times the other part, the derivative of the other part. And it works out like this. The derivative of 3x squared means 3 times the derivative of x squared. The derivative of x squared is 2x. And so 3 times 2x, 6x. The way you'll use this often is you'll skip this step and you'll say 2 times 3 is 6. X to a power 1 less than that. A lot of times it can be that fast to use this proposition. But sometimes you'll need to go through this step as well. Let's look at some examples. G of x is 6x cubed. This one we can do very quickly. 6 times 3, 18. X to a power 1 less than that. So 18x squared for the derivative. Very, very quick like that. Now notice, understand though, that it's really 6 times the derivative of that. And very quickly we got to this. All right, in this one, f of t is 4t squared over 5. Well, I would begin this problem by rewriting the distinct coefficient. When fractions become involved or other convolutions occur, then we might want to separate out like this. You see, and if there's any difficulty in multiplying the 2 times whatever makes its appearance here, then I would go through a step like this. I would say if we're going to take the derivative, then we would have, now let's just leave this alone for a moment and think about the derivative of t squared. Well, it's 2t. Now think about multiplying those two. See, separate the parts of the problem when the situation gets a little complicated. All right, so here we would have 8t over 5, and another way to write it would be 8/5 t. Here's one where, let's see, we have y and a fraction. Let's expand and rewrite a little bit. 2x all cubed means 2x times 2x times 2x, that's 8x cubed. And we can write this, we can kick the x into the numerator by writing it as x to the negative 3. We could think of a distinct coefficient as 5/8 times this x to the negative 3. Now we're ready to take the derivative. And the derivative is, well, let's see. We think of the fast way is negative 3 times 5/8. That's negative 15/8. X to the negative 3 minus 1, that's negative 4. And then the x to the negative 4 runs down into the denominator to become x to the 4th in that denominator. So our fraction then looks like this. But if there's any difficulty seeing through this, think of the separation of 5/8 and then take the derivative of this part and multiply the two, and you'll get to the same result. Here's another one. Another idea is the sum and difference rules. Sum and difference rules. It is this, that the derivative of the sum or difference of functions will give the sum or difference of their derivatives. You see, you just take the derivative of each one, add or subtract whatever the indicator happens to be. And this becomes this along with the other rules that we've been talking about, the power rule, the constant multiple rule, gives us a way to very quickly deal with derivatives of polynomial functions. Look at this. It's f of x is this long polynomial function. Now, it is not so much that we have separate functions that are being given to us here like the definition sort of implies. It is that we can take our function and we can think of it as this as a function, and that as a function, and that as a function, and that's a function, and that's a function, you see. And so we can add and subtract as we go along with these little functions within our function. That is, if we have a function composed of various terms like this, we can think of each term as a separate function, so we can apply this sum and difference idea and just take the derivative of this term. Derivative of this term. You see, subtract the derivative of that term, add the derivative of this term, subtract the derivative of that term, and away we go. So very quickly it is 4x cubed. Now this one, 3 times negative 2, that's negative 6x squared. 2 times 5, 10x. Let's see, the derivative of the x now to the 1 power is simply 1, so we have this becomes negative 4, and then the derivative of 7 is 0, so it goes out. So here very quickly is the derivative of f. Here we have a g function. Now notice that in the first part of it we have a little convolution in this term. So when that happens, I suggest you burn a step and rewrite and try to make things a little simpler to see through as we go through the derivative process. So I would burn a step like this, and I would write this as negative 1/2 x to the 4th and bring down the other terms. And now it's pretty easy to see through, and I'm going to just go right directly at it with the derivative as, let's see, 4 times negative 1/2. You see, we can see through this. 4 times negative 1/2, that's negative 2. So we have negative 2, x to an exponent 1 less than that, cubed. 3 times 3, 9, x squared. And then 1 times negative 2, negative 2, x to the 0, which is 1. So here's our derivative. Sine and cosine functions have derivatives that are particularly easy. The derivative of sine is cosine. The derivative of cosine is negative sine. Let's take a look at the graphs of sine and cosine together. And in that way, we can see why the cosine is the derivative of sine, or at least I think we should be able to see that. Here's the graph of the sine function. just in one period of the sine function, and I'm going to overlay the cosine graph. And now think about, and in fact as I'm drawing this, you might want to be thinking about what derivative means and the interpretation of the graph of the derivative of the sine function, you see, as the cosine function. Think about that for a second as I go through and draw this graph. You see, the idea is that a derivative is slope of tangent line. And if you think about, here's our function now, and here's the derivative function. And we're thinking a tangent line, and I'm just going to use my finger here as tangent line. What's the slope of the tangent line here? Well, it turns out to be 1 at the very beginning point, and that's why we have 1 here on the derivative function. And then as it goes over like this, the slope of the tangent line is decreasing, you see. And then as we get to this point, it's flat, 0, and then it goes into the negative area, you see. So, and as we start to slope down this way, as we are going downhill, that slope is negative. And as it gets to this point, it turns out to be -1. And this should be right under here, right about here, I guess, from your perspective. All right, so it should be -1, and then the slope begins to level off again, so it begins to come back to 0. Remember, it's negative here, but still it is starting to flatten out. We get smaller and smaller negative numbers. Yes, we do. You see, so we're increasing with that slope through here, and then as we get right to the bottom, our slope is horizontal, and so we get at 0 for our derivative function. And then as we go up this way, we are increasing the slope all the way up to a slope of 1 right here at the end of the period. So that's the idea, and that's how we might investigate. You should do this from time to time, is investigate a function and its derivative from the standpoint of slope of tangent line through some kind of interval. Well, to find the derivative of certain functions, if y is x cubed minus 2 sine x, then to take the derivative of y, we simply think, well, what's the derivative of this term? What's the derivative of that term? We're going to add the two terms. So let's see, the derivative here would be 2x squared, and the derivative, let's see, of this, now using our constant multiple idea, it's 2 times the derivative of sine, which means 2 times cosine. So this is just 2 cosine x. And here's another one. Here's another y. So the derivative of this means the derivative of this term, which is 2x, times the derivative of this term. That's -1/2 times the derivative of cosine is negative sine. So this becomes plus 1/2 sine for this part of the problem. So it's relatively easy to deal with functions that involve sine and cosine. We'll get to the other trig functions in the next section. Well, let's talk about a couple of problems. This one says to find the slope and the equation of the tangent line to the graph of this function at the point 218. Well, let's see. If we start talking about slope and tangent line and that kind of thing, we're talking about derivative, so we want to take the derivative of y. And before we do that, though, we might want to simplify y. So we might want to write y as, let's see, 3x times x squared, that's 3x cubed. And then 3x times minus 2 over x is minus, let's see, 3 times 2 is 6, and the x's look like they're going to cancel. So it's 3x cubed minus 6 for that function. Now the derivative then is 3 times 3, 9x squared. Is that all there is to it? Well, I guess so. Now, what about the slope of the tangent line at that point? Well, that point has an x of 2 and a y of 18, but that's on the graph of the function. The slope of the tangent line at x equals 2 is found by just taking, if this were in the form f of x, we're taking f prime of 2. So we're taking y prime at the point 2. So that y prime turns out to be y prime at the point 2, you see, turns out to be 9 times 2 squared, or 36. So the slope of the tangent line at that point turns out to be 36. And that's all we had. This is all we had to do to calculate that. In the previous section, we had a lot more to do, a lot more manipulation to do to calculate the same stuff. Well, what about the equation of the tangent line? Well, that's no big deal either, because we go to our y minus y1, our point slope form, and fill in. So we would have, let's see, y minus, now a point, the point we're talking about is this point, and the slope we're talking about is the slope of the tangent line, which we just calculated to be 36. So we have y minus 18 equals 36 times x minus 2. So it's y equals, now I'm going to kick the 18 over at the same time that I multiply here, 36 times x, 36x, and then 36 times minus 2 is minus 72, and then plus 18. So 36x, let's see, minus 72, minus 54. So here's the equation then of that tangent line. So again, the problems that we encountered before become ever so much more simple now that we have these rules for finding derivative rather easily. Now, you might be asking yourself, why does this derivative, why are we studying derivative? What use does it have? What can we do with this? What kind of power has come to the mathematical table for us in this matter? Consider this problem. This is an equation that it's sometimes called a position equation, but the position has to do with the height of an object, so I'm going to try to make this relatively easy to imagine by thinking of this as a height equation. It's the position as the height of an object that is either dropped or thrown into the air or something like that. It has no power behind it. Just the power of gravity is moving that object. But here's how the equation works. 1/2 gt squared plus v naught t plus s naught. Now, what do all these letters mean? G is the acceleration due to gravity. The acceleration due to gravity is negative 32 feet per second per second. Or in metric terms, it's negative 9.8 meters per second per second. Now, I'm not stuttering there when I say negative 32 feet per second per second. I mean it's negative 32 feet in the first second, and then another negative 32 feet in the second, and so on. And it just kind of increases its acceleration in a rather linear fashion that way. So after a couple of seconds, it would be negative 64 feet per second, you see, and that kind of thing. So it's increasing speed all the time. We're neglecting the idea of air resistance here just for a moment. This wouldn't work well with a feather, but it would work great for a cannonball. Okay, so let's see. That's the acceleration due to gravity. T is time in seconds. V naught is initial velocity. So there would be an initial velocity if we were talking about throwing a rock into the air or someone jumping on a trampoline or something like that. There would be a velocity going up if the person is jumping upwards. If we're throwing a rock downward, then the velocity would be downward. If we're just dropping something, the velocity would be 0. Okay, then S naught is the initial position, the initial height in this case. And incidentally, this equation appears in your textbook, and it is S, a function S in terms of t is the way it's listed in the textbook. I'm listing it as height because it's easy to imagine the situation in that way. For an object dropped from 144 feet, now we're dropping the object, so V naught would be 0 and S naught would be 144. And if we're talking about feet in the air, then we're going to use the acceleration due to gravity as negative 32 feet per second per second. So replacing in our equation, we have 1/2 times negative 32 times t squared times 0t plus 144, or negative 16t squared plus 144. Now, the relationship then between height and time we can put onto a graph if we want to, kind of like this. If we put height on the vertical axis and time on the horizontal axis, then we can sort of plot where this object will be when it's dropped. We would start here at 0. The object is at 144 feet. and then after 1 second it's dropping a bit, and after another second it's dropping a bit, and it turns out that after 3 seconds the object hits the ground. So the graph then might look something like this. I know it's a parabolic curve that's opening downward, and it has a vertex at this point, so it kind of maybe looks like this. All right, good. Now, height and time. Think for a moment about a tangent line and the slope of the tangent line and the interpretation of the slope of the tangent line at a point on this graph. Now, what are we really talking about here? Well, let's see. If we're thinking about the slope of a tangent line at a certain point, we know from our previous work that the slope of tangent line at a point means something like h prime, see, the derivative at a point for this function, the derivative at a point is h of t minus h of the point, and over t minus c. You see, if that point is c. Now, so that's just kind of a general idea. Now, what are we doing here when we calculate h of t minus h of c? H of some place here minus h of our target point. What are we talking about? Well, we're talking about a height. You see that those h of t means height in terms of time, so those are vertical distances. So vertical distances, the vertical axis is a height. So this is just nothing but a change in height. So it's a delta height, if you will. And that's just some distance, you see. Some vertical distance is what we're talking about. Now, t minus c, if we're talking about horizontal values here, horizontal axis is the time axis. So this is just some change in time. Now, so we have a change in height over change in time. Distance over time. Distance over time, that kind of rings a bell. Distance, time. Oh, we had a relationship involving distance, time, and rate. That relationship was, come over here and I'll write it down. That relationship was distance is rate times time. Now, we're talking distance over time over there. Gee, if we divide on both sides by time here, we have this. So rate is distance divided by time. Rate, speed, velocity. Similar ideas. Speed is always positive, though, regardless of what direction you're going in, and velocity can have a negative attribute associated with it, so we're going to call this velocity. So h prime at a point is nothing but a velocity. And in general, the derivative function of this position equation or position function is a velocity function. You see, this is nothing but a velocity function that's associated with this original function. Now, let's stay with our problem here just a little bit and think about a couple of matters associated with it. Let's say we want, instead of velocity at a particular point, let's talk first about average velocity along an interval. You see, along an interval. We can think about the interval from 0 to 1. You see, in this interval, what's the average velocity? Average velocity would be like the average slope of tangent line idea, you see, in that area, in that region. And from 1 to 2, we could think about from this point to this point, we could think about average velocity as the average slope of the tangent line, that kind of thing. Well, you know, we can calculate that, and it's not too difficult. And it works kind of like this. For the average velocity from, let's say, t equals 1 to 2. From 1 second to 2 seconds, let's calculate average velocity. Average velocity is the difference in the height over the distance in time. So that average velocity is, let's see, difference in height. The height when t is 2 minus the height when t is 1. That's the change in the height, you see, or the position, vertical position for that object being dropped. And then over the difference in time. And the time of 2 seconds minus the time of 1 second. The difference in time is just 1. We're talking about a 1 second interval here. That makes sense. Now h of 2, in the h function, we pop in 2 and we find 80. So after 2 seconds of dropping from 144 feet, that object is at 80 feet. You see, and after 1 second, that object is at 128 feet. So 80 minus 128 is negative 48, so the average velocity within that interval is negative 48. Average velocity within the interval. What about the velocity at t equals 1 second and the velocity at t equals 2 seconds? You see, how fast is the object going after 1 and 2 seconds? Let's come back over here and make the calculation. Now we're saying that the velocity equation is nothing more than the derivative of the height equation. So if this is the height equation, if this is our height function, then our velocity function, our v in terms of time, is nothing more than h prime of t. And h prime of t is the derivative of this, which is, let's see, 2 times negative 16, that's negative 32 t, and the 144 goes out. So it's simply negative 32 t. So if I want the velocity after 1 second, then that is the same as h prime of 1, you see, or negative 32 times 1, negative 32. So the velocity after 1 second is negative 32 feet per second. That makes sense. After 1 second, we drop the object, and after 1 second, it's going 32 feet per second downward. That fits with what we talked about as the acceleration due to gravity. We said the acceleration due to gravity is negative 32 feet per second per second. That must mean that after 2 seconds, it's going to be going twice as fast. Well, let's see. The velocity after 2 seconds is the same thing as h prime of 2. So in the h prime function, which is this, replace the t with 2, and we have negative 32 times 2, that's negative 64. Aha, that's exactly what we kind of expected it to be. Well, so the notion here is that a derivative function can give some very real extra information given an original function. So you have an original function, or an original relationship between two variables, and that derivative function has great power in analyzing certain aspects of that original function.